Hi, I'm Mr. Gru, and we are going to be talking about zero knowledge proofs, the origins for Montessori students. This is the absolute beginning of zero knowledge proofs, and we are going to start from the very basics, how everything started. Yes, that's me. I'm evil as anyone can get. Now, to understand the origins of zero knowledge proofs, we have to understand something called NP hard problems in computer science. Why is that? Because zero knowledge proofs were first, conceptualized with NP hard problems in mind. And let's have a look at them. Now, in theoretical computer science, we classify difficult problems according to their complexity. Okay. So the first class is P, which is polynomial time, which are easy to solve. And then there are NP problems, which are non-deterministic polynomial, which is a very convoluted term, but it basically means that they take exponential time to solve and they are very difficult to solve. There are also NP hard and NP complete sets, which are extension of NP class, which we use to express more sophisticated problems. So, in a sense, we can say that polynomial problems are easy, NP problems are medium difficult to solve, NP complete problems are hard to solve, and NP hard problems are the hardest problems of all. This is what it looks like. P is polynomial, easiest at the bottom, NP, which is medium, NP complete, which is hard, and NP hard, which is the toughest of them all. Now, how much time does it take to solve a problem can be expressed, in some mathematical form, where we say that the order of the solution is such and such. So if the order of the solution is 1, which means it takes a constant number of steps or time to solve it. For example, addition of two numbers or subtraction of two numbers. If you want to add 1 plus 1, you take one step and that is 2. Now, if it takes logarithmic time compared to the number of variables in the problem, then it is, of logarithmic complexity. If it takes, in the worst case, n time, n steps, where n is uh, the number of variables in the problem, so that is linear time, so on and so forth, n square, n to the power k is polynomial, still easy to do. It is considered easy. K to the power n is exponential. It is impossible to have an exponential amount of resources, compute resources, and time and storage. So these are impossible problems to solve. And n factorial is also prohibitive to solve because it grows to very large numbers very, very soon. Now, what are some examples of such problems? NP problems are basically problems which cannot be solved in polynomial time, which means they take exponential amount of time or more. However, they can be verified in polynomial time. If somebody gives you a solution, you can verify the solution in polynomial time. For example, integer factorization. If you want to factorize 15 into 3 and 5, it might be very difficult to solve. But if somebody gives you 3 and 5, you can multiply them together and get 15. So you can verify very easily in polynomial time that 3 and 5 are in fact the factors of 50. Similarly, there is a problem called graph isomorphism, which basically deals with the problem of whether two graphs are the same. Then there are NP complete problems. These are very similar to the previous set. There are more than 3,000 of these problems in computer science, and computer science community is adding more and more problems to this list. What makes this different from NP problems is something called completeness. If you have a NP complete problem, any NP problem can be transformed into it and solved, assuming you can solve it in you can somehow solve it in polynomial time instead of exponential time, but every NP problem can be transformed into an NP complete problem in polynomial time. This transformation is also called reduction. Some examples of NP complete problems are knapsack and graph coloring. We are going to look at graph coloring in a bit. Then the last category is NP hard. These are the most complex problems in computer science. They are not only hard to solve, but very hard to verify as well. If somebody gives you a solution, you cannot verify very easily whether that is in fact the solution. Some of these problems aren't even decidable. They are k-means clustering and traveling salesman problem. Let's understand the traveling salesman problem. If you have n, places and you need the shortest route between them, not only is it exponentially hard to solve this problem, but also if I tell you that this is the shortest route, how will you verify that it is in fact the shortest route without completely solving the problem, yourself? If you could do such a thing, like solving the problem. So NP hard problems are the most toughest of the problems in computer sciences. Now, in 1980s, MIT researchers Shafi, Goldwasser, Silvio, and Charles were working on problems related to interactive proof systems. There used to be a party called the prover, and there used to be a second party called the verifier, and the prover would try to convince the verifier that some mathematical statement is true. Obviously, in cryptography and computer sciences, you are going to prove a mathematical statement is true. If you have to prove like a layman's assertion that Bob is my friend, you have to somehow convert it into a mathematical statement and then prove it. That which, if proved, would imply that Bob is your friend. Now, prior to Goldwasser, most of this work in this area was focused on the soundness of the proof. What is the most accurate way of proving, etc. And uh, people were focused on whether, a, a malicious prover attempts to trick the verifier into believing a false statement. Now, Goldwasser, Micali, and Rakoff turned this problem on its head, and instead of worrying about the prover, they asked what happens if you don't trust the verifier? How much information are we leaking to the verifier? What about our privacy? How is he going to use all this information? So, we the problem was then phrased as what is the way of proving something to a verifier without disclosing too much or any information other than the assertion that my proof is true. I know something. Bob is my friend, and so uh, that was the origin of zero knowledge proofs. Now, if you have a graph like this, there are some nodes and there are some edges connecting, the nodes together. The graph coloring problem is basically a problem where you limit the number of colors you can use. Let's say two, three, or whatever. Here we have three colors: green, red, and blue. And you are supposed to color the graph in such a way that no two adjacent edges, adjacent nodes have the same color, which means there is no conflict. So if you see on this graph, pick any two nodes that are connected by an edge, they don't have the same color, which means that this is a solution to the graph coloring problem. Now, how do you solve this problem? There is a telecom company which wants to deploy a cellular communications network, and they have this graph of whatever, island, and there are towers put there. These nodes are the locations of the towers. Okay. Let's say this is some island and this is the geography of the island, and this is how the towers are arranged. Now, the connecting lines indicate that there is some overlap between the ranges of two towers, and the transmissions might interfere with each other. As you know, if you have the same frequency, if two of your friends use the same frequency on the radios, their radio sets will interfere with each other. So this is a kind of an interference graph where you have to figure out a way of, designing the cellular network. Now, obviously, the solution is to assign frequency bands to towers such that no two overlapping cells share the same frequencies. Uh, the most obvious solution is to give, if you have infinite frequencies available to you in your band, you could simply assign each tower a completely different frequency. But what if the number of frequencies were limited in your band and we could assign only two or three frequencies or 10 or 15 or whatever? Now, can we assign frequencies to these towers so that there are no overlapping, conflicts of frequencies in adjacent towers? If we use colors to represent the frequency bands, we can probably, try to, figure out a solution because colors are more, easy for us humans to understand. So we represent each frequency by a different color and try to assign colors to these towers. But then some of you will realize that this is simply a three graph coloring problem where you're using three colors. And this, while this might be easy uh, in this case to solve it, but in a real world example of a graph coloring problem, it is quite hard to find a solution or even to figure out if there is a solution which exists. Now, let's say this is a very difficult problem, and the size and complexity is huge, and the telecom company is not able to solve it. It does not have the computing resources or whatever. And uh, you know, one thing it could do is it could hire somebody like you or some other company or you to solve this problem for them. But this leads to a problem. Suppose you spend a lot of money and compute resources in solving this problem, and you finally arrive at a solution of coloring this network of towers. The telecom company is not going to pay you until they know that you have solution, a valid solution. At the same time, you are not going to give up your solution to the telecom company unless they have paid up. So we'll end up at an impasse. But how can you prove that you have a valid solution to the telecom company without disclosing your solution? Let's say this is the solution that you have, but now how would you, prove it to the telecom company without disclosing your solution? And this was the problem that, which people were trying to solve in 1980s. How do you uh, prove that you have a solution to a graph coloring problem, which is NP complete? So, which in a sense means that how do you prove that you have a solution to any NP problem without disclosing the solution itself? Now, here's how you'll do it. The first step is called a random commitment. You are the prover. You will color the graph completely in some order using red, green, blue, or green, red, blue, or blue, red, green, sequence of colors. And you will solve it and you will commit to the verifier. Now, once you commit to the verifier, you can't change the colors. Okay. That is somehow we have to figure out how it needs to be done so that you're not able to change the solution. You can somehow hash the solution together so that you put the hash on a blackboard, and so obviously you can't change it later. Okay. Now, the second step is a random challenge by the verifier, which says the verifier says, okay, I mean, I don't want to know your entire solution. I will not ask you to disclose each and every, the color of each and every node in the network. But here, show me the colors you have assigned to just these two nodes. And so he picks nodes 7 and 8, let's say, for example. Okay. And then you respond to the random challenge by the prover by disclosing the color of just these two nodes, 7 and 8. And the verifier verifies that they are not of the same color. So there is no conflict. The entire problem in graph coloring is to assign colors with absolutely no conflicts. So assuming you had a solution, to the graph coloring problem, if somebody picked any two adjacent nodes, they should not have any conflict. Even a single conflict will violate the sanctity of the solution, right? So here he picked 7 and 8, and you showed that, you know, they have, purple and blue colors, and they are not in conflict. And we do this process again and again. You again color it using some random sequence, RGB or BRG or whatever, so that you make a random commitment. Then he again challenges you, and then you again respond to the challenge, and so on. This is how you prove that to a sufficient degree of probability that you have, in fact, a solution to a NP complete problem, which is graph coloring. Now let's take a step back. Most zero knowledge proofs, interactive zero knowledge proofs, tend to have the same three-step structure. The prover first generates some random values and creates a random commitment and sends it to the verifier. The verifier responds to the challenge value generated randomly, and the prover computes the final proof based on both the random commitment he committed initially and the challenge that the verifier has thrown at him. And that is how most interactive zero knowledge proofs work. Now, nobody can solve NP problems. And also, since graph coloring is NP complete, any NP problem can be converted into graph coloring problem in polynomial time. Which means this zero knowledge proof scheme can be used to prove and verify the solution to any NP problem without the prover having to disclose the solution to the verifier. Remember, in this case, there were random challenges and responses in the protocol. Hence, this was a type of interactive zero knowledge proof. In the next presentation, we are going to see how we make non-interactive zero knowledge proofs. This is exactly how zero knowledge proofs were invented, how scientists thought about proving, some mathematical statement without disclosing the solution. This is the origin of zero knowledge proofs. I told you I was evil, didn't I?